Welcome again. We're going to be looking at power this time. So power, one of our last topics in this particular chapter for physics. We've been looking at work and different types of energy, etc. Power, when you look at it in a physics sense, and it's related to what you would talk about with power in a general sense, but power is the rate of doing work. It's not just about what work is accomplished, but how quickly is it accomplished. So if you walk up a flight of stairs, or if you run up a flight of stairs, you'd be doing the same amount of work because you're going that same force, basically lifting yourself against gravity to go up the stairs. Same distance because the stairs are the same. So that's the same amount of work. But if you're running up there, you're doing it at a faster rate. That's going to require more power from your muscles, from your body, etc. So when you're looking at power, that rate of doing work, that gets measured in watts, which is abbreviated as a capital W. You've heard of that probably when you talk about light bulbs and stuff like that. That measure of how much energy does that light bulb using. That's your energy, your joules per second. It's sort of unfortunate that the unit is watt because when you talk about the rate of doing work, well, when we're in an equation, our variable work is usually represented by a W. But then the unit for power is going to be also a W. So they're the same letter, but one is a variable representing something in an equation, one's a unit. So they shouldn't get too confused, but it is sort of unfortunate that they are the same. So our main version or main equation when you're talking about power, since it's the rate of doing work, anytime you're talking about a rate, it's whatever that is per time typically. So power in our general form is going to be work divided by time. Take that work, you divide it by time. That's the one you'll use probably most of the time. But if we do look at work, if you're to think about work as being force times distance, I'm not going to write it on the screen here, but we have force times distance over time. And distance over time, well, that's velocity. That would just be an average velocity or a constant velocity. So another version we could have if we take that force and then distance over time is that power would be force times velocity. And that would be only true if you're going at a constant velocity. If something's accelerating, changing that velocity at all, that second equation there would not work. But if we are at a constant velocity, you could use that version force times velocity. That would also give you power. So you got those two with that disclaimer on the second one that it has to be a constant velocity, no acceleration allowed. So let's take a look at an example dealing with power. We want to know how long will it take if we have a 1.2 kilowatt motor to raise a 1,250 kilogram car 2.0 meters. Maybe it's hooked up to like a hydraulic jack or something, or a lift or a pulley system or something. I don't know exactly what. Let's say it's a pulley system. In your car, you're lifting it up with a winch there on your motor. A 1.2 kilowatt motor. It's going to raise that 1,200 kilogram car 2 meters. So talking about work. We want to know how long. So our equation, power equals work over time. We're trying to find time. Okay, that's right there. We know the power, 1.2 kilowatts. So what about that work? Can we plug something in for that? Work, if we look back, think back to the beginning when we first talked about work, and we mentioned it just a moment ago. Work is force times distance. Okay, I know the distance, 2 meters, getting somewhere. What about the force? If we're raising a car, what would that force be? Hopefully, you're thinking about it. Maybe you're saying it out loud and embarrassing yourself in front of the rest of the class. With that force, when you raise something, you're overcoming gravity. So if we're lifting something, raising something, that force involved would be equal and opposite to gravity. So we're looking at our force being mass times the acceleration due to gravity, and then times our distance for that work. So I think now we know everything except for time. We know the power, we know the mass, we know g, we know our distance. So at this point, we've got our equation all beautifully set up, and we can go ahead and plug everything in. Let's plug in our power, our mass, our gravity, and our distance. Do note I didn't put in 1.2, I put in 1,200 for my power, and that'd be because if you look back at the problem, it's 1.2 kilowatts, and we want to put in our base unit of watts, so 1,200 when I plug that in. And then if I do a couple things here, I'm going to multiply the T, multiply that over to the other side here, so that it's not on the bottom anymore, and then I'll just multiply all three of these together to get a single term. So now I've got 1,200 T, and when I multiplied 1,250 times 9.8 times 2, I got 24,525. Last step then, if I want to get t by itself, I would divide both sides by 1,200. And if I do that, and with looks like 2 sig figs on those two numbers, 3 on that, so 2 sig figs for my final answer, I would get about 20.4, etc. So that would round off to 20. And if I want it to be 2 sig figs with 20, I'd have to put that decimal point on there, 20 point, and then seconds. Otherwise, you could write it as 2.0 times 10 to the 1 seconds, but 20 with a decimal point would work well for our 2 sig figs. So that's at least one type of example working with power. Most of them are hopefully reasonably straightforward. So we'll see how that goes for you. Good luck. Get going on your assignment, probably, I suppose, maybe. And we'll talk to you whenever it happens to be that I talk to you next.